Hello, welcome to Beneath the Curve. Today, I would like to share with you a beautiful result in group theory known as the first isomorphism theorem. This is a result relating groups and homomorphisms between them, and is summarized here with this commutative diagram. So let's break it down. Here we have two groups, G and H. Phi is a homomorphism between them. G mod kernel of or phi is a factor group of G. Phi of G is the image of G under phi. What these relations are telling us is that, first of all, phi of G is a subgroup of H, and G mod kernel of phi is isomorphic to phi of G, which is what we are going to see today. So, first of all, we have to see that the kernel of phi is a normal subgroup of G, so that G mod kernel of phi is actually well defined, because recall that factor groups only arise from modding out normal subgroups, else they don't make sense. So doing this is a simple task. As you see that, well, to show that the kernel of phi is a subgroup, normal subgroup of G, it suffices to show that for all G and G, G kernel of phi, the inverse is kernel of phi. Oh. That is, if we take an A in the kernel, then we have to show that G, A, G inverse is also in the kernel. To this end, let's consider phi of G, A, G inverse. This is phi G, phi sorry. This is phi of G, A, G inverse equals phi of G, phi of A, phi of G inverse using the homomorphism property. Since A is in the kernel of phi, we know that this is equal to the identity of H. And so this is phi of G times phi of G inverse, which by the homomorphism properties phi of G, G inverse is phi of the identity of G, which is obviously the identity of H. All right, so since phi of G, A, G inverse is the identity, it follows G, A, G inverse is in the kernel of phi. Therefore, we have G kernel phi, the inverse equals kernel phi, and so kernel phi is normal. Since it's normal, we can say that G over kernel phi makes sense. Okay. Now, for good measure, we will show that phi of G is a subgroup of H. Now, this is really easy, but clearly phi of G is a subset of H, since, well, every element of phi of G must be in H by the definition of the homomorphism, since it's mapped from G to H. Okay, so since it's a subset of H, to see that it's a subgroup, it suffices to check that if G and H are in H, then GH inverse is in H as well. This is sufficient to show that phi of G is a subgroup. Well, but this isn't too complicated. If we grab A and B and G such that phi of A equals G and phi of B equals H, then we may observe that phi of AB inverse times phi of B is equal to phi of AB inverse B by the homomorphism property is phi of A. Then multiplying by the inverse of phi of B on the right, phi of AB inverse equals phi of A, phi of B inverse, which by our above mentioned equalities is GH inverse. Thus we find that phi of AB inverse equals GH inverse, so GH inverse is in phi of G as well. Voila. Okay, with this settled, we will now show the beauty of the isomorphism theorem, the first isomorphism theorem, which is that indeed G mod kernel of phi is isomorphic to the image of phi. This is really useful, and you're going to see why. So, to show that they are isomorphic, we will provide an isomorphism. So consider the map psi going from G mod kernel phi to phi of G, given by the following. The left coset A times kernel phi is mapped to phi of A. Okay, first of all, we should check that this map is actually well defined. So let's begin with this. Well defined. So if A times kernel phi, left coset, is B kernel is equal to B kernel phi, we must see that the image of both of these is the same, so that the map is actually well defined. Well, this implies that A inverse B is in the kernel of phi, by definition. Okay. Therefore, phi of A inverse B is the identity. Hence, phi of A inverse times phi of B is the identity, multiplied by phi of A on the left, phi of A inverse phi of B equals phi of A. But of course, phi of A times phi of A inverse is just the identity. So this gives phi of B equals phi of A as decided. Hence, this map is well defined because we map the same thing to the same thing. All right, now we will show this map satisfies the homomorphism property. And since I'm tired of writing a kernel phi, I'll just let K equal kernel phi to abbreviate notation. Okay, so then psi of AK BK equals psi of ABK, since the kernel is a normal subgroup, we can do this. Now this, of course, equals phi of AB. Since phi is a homomorphism, by the homomorphism property, this is phi of A times phi of B. But then phi of A is just psi of AK, and phi of B is psi of BK. But this right here is exactly the homomorphism property. All right, now I show that this homomorphism is injective, also known as one-to-one. So to this end, suppose psi of AK equals psi of BK. Then phi of A equals phi of B. Then, by similar work as before with the well-defined property, this implies that phi of A inverse B is the identity. Thus, A inverse B is in the kernel. Okay. Since A inverse B is in the kernel, we can see the following. BK will equal A inverse B. Okay. Now, for all K in the kernel. Now, since the kernel is a subgroup, that's a group, we know that this is in the kernel. Hence, what we're saying is that the left cosets of the kernel, the left coset of the kernel by B is the same as the left coset multiplied by A. However, this is exactly the definition of injectivity. Having the same image means they are the same thing. All right. Finally, surjectivity. This one's really easy. If you have a phi of A in phi of G, then you can, well, just psi of A equals phi of A. Well, this shows surjectivity. So psi is a homomorphism, injective, and surjective, so it's an isomorphism. And this shows beautiful result that G mod kernel phi is isomorphic to the image of phi, where phi is a homomorphism. All right, there are two special cases that we can analyze. If you see our first isomorphism theorem, you see the commutative diagram looks like a rectangle. However, this rectangle can be simplified when phi is either surjective or injective. If phi is both, then phi is an isomorphism, and there's not much to analyze. It's just telling us G is isomorphic to H. But just surjective or just injective gives interesting results. So let's start with what happens if phi is surjective, which is actually the most common application of the isomorphism theorem. Well, if phi is surjective, this just means that phi of G is precisely H. So what this tells us is that G mod the kernel of phi is isomorphic to H. And this is super useful when we're trying to show that a factor group is isomorphic to another group. The big idea is to find this relationship. We go from, well, if we're trying to show general groups, say M mod N is isomorphic to L, then we want to find a nice homomorphism phi such that phi is surjective. Phi goes from N to L, and its kernel is N, because then we can apply this first isomorphism theorem in this special case where the homomorphism is surjective, and this will give us this relationship between this factor group of M and L. Now, second case, which is also notable, but I've not seen used as much, is what happens when phi is injective. When phi is injective, it's easy to see that the kernel of phi is trivial. It's simply the identity. Therefore, G mod kernel of phi, which is just G mod the identity, is isomorphic to G. And so G is isomorphic to phi of G. As we saw before, phi of G is a subgroup of H. So if we find the homomorphism that is injective, mapping from G to H, what we have shown is that G is isomorphic to some subgroup of H. This, I imagine, has its explications, but I have not seen it used very much. So let's see some examples of utilizing this theorem. First, we will show that Z mod NZ is isomorphic to the cyclic group with n elements. Of course, Z mod NZ is a common notation for the integers mod n, which is exactly what a cyclic group with n elements is doing. So to this extent, let G be a generator of Cn. That is, Cn is generated by G. Then we will define the following homomorphism in light of the first isomorphism theorem. Phi going from Z to Cn given by an integer m is mapped g to the m. All right. So first, it's clear that phi is a homomorphism, because phi of m plus n equals g to the m plus n equals g to the m, g to the n. It's phi of m, phi of n. So it satisfies the homomorphism property. Second of all, if we have g to the k and cn, then phi of k equals g to the k. So phi is surjective. Phi is surjective. So you just have to analyze the kernel of phi and hope that it is nz, so that we can apply the first isomorphism theorem. Well, indeed, the kernel of phi is the set of integers m such that the order of g divides m. But the order of g is n, by definition of the subgroup. Therefore, this kernel of phi is precisely those integers that are divisible by n, i.e. nz. Thus, by our all-powerful first isomorphism theorem, we can say that z mod nz is isomorphic to Cn. Let's look at another example. We'll show that the Cartesian product of g times h has a factor group that is isomorphic to g. Indeed, the idea is the same. The factor group will be g times h mod the kernel of some homomorphism. So we try to set up this homomorphism phi and g times h to g in such a way that phi is surjective. So one obvious choice for this homomorphism might be gh is mapped to just g. Okay, so first it should be clear that this is a homomorphism because we have phi of g1, h1, g2, h2. This equals phi of g1, g2, h1, h2 equals g1, g2, which is phi of g1, h1 is phi of g2, h2. All right. So this establishes homomorphism property. It's surjective because for g and g, let's take phi of, this is just g. So it's clearly surjective. And finally, the kernel of phi is precisely those elements that look like the comment h, some h and h, as these are the elements that map to the identity, and only these. Hence, by the first isomorphism lemma, g times h, we see that g times h mod e times h, e is the identity of g, this is isomorphic to g, which is what we want to show. In fact, we found by what group we are modding out. And in a much similar fashion, we can show that g times h mod g times e is isomorphic to h. In fact, the proof is basically the same. Right. For our next example, we define the set n as the set of ordered pairs of integers such that both coordinates are the same. I'm going to show that z times z mod n is isomorphic to z. So we want to show we want to find some homomorphism such that the set of integers, the set a comma a of integers is the kernel. So one idea might be to use a sort of subtraction. That is, map a map phi from z times z to z given by a comma b maps to a minus b. Okay, so this is useful because, well, first of all, it's an isomorphism because phi of a comma b plus c comma b equals phi of a plus c comma b plus b equals a plus c minus b plus b equals a minus b plus c minus b, which is just phi of a comma b phi of c comma b. This is precisely the homomorphism property. It's always good to mention these are homomorphisms, since otherwise the first isomorphism theorem does not apply. Okay. Now, why is it surjective? Well, if we have a and z, phi of a comma 0 equals a minus 0 equals 0. So it's surjective. And finally, the kernel of phi is a set of a comma b such that a minus b equals 0. That is n, because we have a equals b, so it's just a comma a. So once more, by the first isomorphism theorem, we have that z times z mod n is isomorphic to z. And finally, for one last cool example, we relate one of the three of the most common sets, which are the real numbers, the integers, and the complex numbers. In this case, we're not using the entirety of the complex numbers, we're just using the complex unit circle, which is the set of complex numbers which have magnitude 1. What this is saying is that you take the reals and you mod them out by the integers, and you obtain a group that is isomorphic to this unit circle. So I want to appreciate how beautiful this is, because what we're taking is take the real number line, 0, 1, 2, -1, etc. By modding out by the integers, what we're essentially saying is just look at the integers, interpret the integers as 0. We don't care about them. And basically everything that is here corresponds to everything here. So when we do this modding out, which looks like we're being solved in cosets, because if you notice, for example, 1/2 is in the same coset as -1/2 or 3/2, etc. It's like looking just at the segment 0, 1. What we're saying is that this, looking at the cosets, this is just like the way to get a picture. It's not very rigorous. You can wrap this around into the complex unit circle. Okay. So that was a very bad explanation about why this result is pretty, but you know, it's basically you're grabbing the real numbers, and by modding them out by the integers, you get this circle. And you can do a similar thing in more dimensions by modding out r squared, etc. And that like spheres and cylinders, and it's very cool. Anyway, for this, again, we want some map from R to the complex unit circle, which I'll just abbreviate by H. So we want this map by H. We want several things from this map. We want it to be surjective, and we want a Z to be the kernel. So since we are looking at the complex unit circle, one idea might be to use these angles, because the complex unit circle, basically what it is a collection of angles. Because multiplying by numbers in the unit circle is just moving around by a certain angle. 1 is angle 0, I is pi halves, etc. So consider the map given by x to e to 2 pi I times x. Okay, why is this map surjective? Take some complex number z and h. Since z is in h and it has magnitude 1, we know that z is equal to e to the I theta for some theta in R. So then phi of theta over 2 pi is equal to e to the 2 pi I, and theta over 2 pi equals e to the I theta, which is z. Hence, phi is surjective. All right. Furthermore, the kernel of phi is the set of x in the real numbers such that e to the 2 pi I x equals 1. This is very clearly the integers. Because when we have this complex number being equal to 1, well, e to the pi to the I theta being equal to 1, theta is a multiple of 2 pi. We already have this 2 pi taken care of here, so any integer x will do the deal, and in fact, only the integer x will be will make this expression equal to 1. So only the kernel. Hence, by the first isomorphism theorem, we can conclude that real numbers modded out by this kernel, which is the integers, is isomorphic to H, which is, again, a superposition. So I hope that this quick and flimsy explanation of first isomorphism theorem along with some examples gives you an idea of why group theory is cool and why this result is super powerful. Thank you and see you next time.